In section 3, we're going to take a look at discrete and continuous random variables. So we're going to start off with an example. So we're going to look back at the example where we tossed a coin 3 times. So there are a lot of different outcomes. Okay. First outcome is 3 heads. Okay. We could get then 2 heads and a tails. Heads, tails, heads. Tails, heads, heads. Tails, tails, tails. Tails, tails, heads. Tails, heads, tails, and lastly, heads, tails, tails. So there are 8 outcomes for flipping a coin 3 times. And then the probability of any one outcome is 1/8. So like the probability that you get 3 heads in a row is 1/8. Specifically getting 2 heads and then a tails is 1/8. If we were to say the probability of getting 1 heads, that changes because there's a lot of different outcomes that have 1 head. So let's take a look at our sample space our sampling distribution. So X is the number of heads out of 3 coin tosses. So X equals 0 is no heads in 3 tosses. And there is 1 outcome, which means the probability is 1/8. X equaling 1 is 1 head in 3 tosses, which exactly 1 heads occurs 3 times. So there's 3 outcomes, which means 3/8. X equals 2, 2 heads in 3 tosses, which happens 3 times, which means there's also a probability of 3/8. And lastly, X equaling 3 is 3 heads in 3 tosses, which there is 1 outcome. So its probability is 1/8. And just to double check, my probabilities do add to 1. 1/8 plus 3/8 plus 3/8 plus 1/8 is 1. Okay, so probability distribution is the probability our random variable takes that value. So when we fill out our table, 1/8, 3/8, 3/8, 1/8. That's just taking what we had above and putting it into the table. Okay. We can also construct a table for this. So the x-axis would be the number of heads. The y-axis is the probability. So 1/8, 2/8, 3/8, and we have 0, 1, 2, 3. So 1/8, 0 to 1, there's 1/8, 1 to 2, 3/8, 2 to 3. Technically this is 3 to 4. So it is a histogram. A probability distribution, remember, does follow a histogram. So what we can do is use this to find probability. So the probability that X equals 2, which is exact, that 2 of the tosses come out heads, is 3/8. We can also look at inequalities. So the next one says the probability X is greater than or equal to 2. So that means you take the probability that X equals 2 and you add the probability that X equals 3. So 3 out of 8 plus 1 out of 8 gives us 4/8, which is the same thing as 1/2. So you have a pretty good chance that if you were to flip a coin 3 times in a row, you're going to get 2 or 3 heads. Now, next one, it says the probability x is less than 2. So that means strictly less than 2. So the probability x equals 0 plus the probability of x equals 1. If it had said the probability of x is less than or equal to 2, then we also would have added the probability that x equals 2. But right now, it's just less than. So that's going to be 1/8 plus 3/8, which is also 4/8, which is also 1/2. So you also have an equal chance that you get less than 2 heads, which makes sense since coins are fair. So that's kind of a review of what we did previously, which then leads us into the next topic. So a random variable takes numerical values that describe the outcomes of some chance process. So we usually use the capital variable X to represent our random variables. Now, random variables can be discrete or continuous, but they have to be numeric in value. So here's where we're going to distinguish between discrete and continuous. So a discrete random variable takes a fixed set of possible values and has distinct values. So usually no decimals and sometimes not every number is an outcome. So the probability distribution lists the values x and their probabilities, and this is done most commonly with a table. So what we just did, flipping a coin, that's discrete. It's specifically landing on heads or tails, depending how you pick it. There are distinct values it can take. So the probabilities related to discrete random variables satisfy 2 requirements. Every probability has to be a number between 0 and 1, and the sum of the probabilities is 1, which is not new information. So, for example, put all the letters of the alphabet in a hat. If you choose a consonant, I pay you $1. If you choose a vowel, I pay you $5. X is the random variable representing the outcome of the experiment. Create the distribution of x. So this is a discrete random variable because there are distinct outcomes for the letters of the alphabet. I would assign them a number so that there is a numerical value associated with it, but there's a distinct outcome. So x in this case is going to be the amount I pay you, okay? So we start with our outcomes and then our probability. So I'm either paying you $1 or I'm paying you $5. So I pay you $1 if there's a consonant. So 21 out of the 26 letters of the alphabet are consonants. And I pay you $5 if you get a vowel. So 5 out of the 26 are vowels. We are not considering Y. Only A, E, I, O, and U are vowels. So it's just an example of a discrete random variable and its probability distribution. Okay. The other type of variable we can have is a continuous random variable. So they take on all possible values in an interval of numbers, and the probability is described by a density curve. So the probability of any event is the area under the density curve and above the values of x that make up that area, and the area under a density curve is 1. So it's kind of similar to what we did with the discrete where we created the histogram, but now we're going to have more specific curve to it. So we're going to take a look at an example. So we have a triangle. Okay. We know the area of said triangle is 1/2 base times height. So if this is a legitimate density curve, what is the height of the triangle? So remember, the area underneath a density curve has to be 1. Okay. So if we're using kind of the height as our y-axis and then the base as our x-axis, we know the area has to be 1. We have 1/2 times the base, which we have a distance of 2, times some height 1. Half of 2 is 1, so 1 equals the height. So we know the height here is 1. Okay. So we want to find the probability that x is greater than or equal to 1. So we're going to go down here. I'm going to go ahead and I'm going to create a new height at 1. So that's basically saying we're going to create a new triangle. This is where 1 is. This is 1 up here. And then this is 2. The probability x is greater than or equal to 1 is basically saying what's the area of that triangle. So our distance, our base is going to be the distance from 1 to 2, which is 1, and our height is 1. So we get 1/2. Okay. Probability that x is 0. So for any continuous function, the probability of exactly a value is 0. So if I had said, what's the probability that it equals 0, or the probability that it equals 1, or the probability equals 2, all of them would have been 0. Because for continuous functions, equaling a value is always going to be 0. Okay. Next, we want to find the probability of x being less than 0.5. So I'm going to go up here in my triangle. I'm going to add 0.5. Which goes up and it goes over. So I need to figure out the height here, which is also going to be 0.5. So we're going to have basically we have 0, 0.5, 0.5. We're finding the area of that triangle. My base is 0.5. My height is 0.5, which is going to give us 1/8. And then lastly, we're going to go to between 0.75 and 1. So this gets a little bit tricky because if you thought, oh, we're just going to go between 1.5 and 1, it'd be a lot easier, but we're adding 0.75, which is between the 0.5 and the 1. We end up with the picture. So 0.751, which then goes all the way up to 1. And then we have 0.75 here. So we end up having a trapezoid, which is hard to see from the way the picture is set up, but instead of the base being the distance from 0.75 to 1, we're going to have the 0.75 to 0.75 and then the 1 to 1. So So we're going to have area equals 1/2. So base 1 is going to be our 0.75 plus base 2, which is 1, times the height, which is going to be 0.25. So our height is going to be the distance between 0.75 and 1. So a little bit different than the last problems where our height was always, well, whatever the height we were looking at was. So 0.75 plus 1 is 1.75 times 0.5 times 0.25, which is going to give us 7/32. Not likely to give you a lot of problems like that last one. Most of the other problems are going to be similar to B, C, or D. So when it comes to discrete and continuous random variables, so equal to does not matter for continuous. If it says equal to or equal to, greater than or equal to, doesn't matter. They mean the same thing. Equal to does matter for discrete though. And it's because, again, continuous random variables don't have exact numerical values, whereas discrete do. So discrete random variables are often described with a table or a histogram, and continuous can only be described with a density curve. So with discrete and continuous random variables, we can find a mean and standard deviation for each of those. So just kind of remember, x for discrete random variables, x equals the numerical outcome of our random event. So in order to find the mean, which we also represent of E of x, we call that the expected value of x when many trials are run. So you're going to see the word find the mean, and it means the same thing as the expected value. You might also be told find the expected value, and it means the same thing as finding the mean. So these are very interchangeable words for discrete and continuous random variables. So to find the mean, so we go back to our table. So if you have your table, you have your values x1, x2, all the way up to xn. You have your probabilities all the way up to whatever your probability is. The formula for mean is to multiply the value by its probability. Okay. So the way you see this written is E of x equals the sum of I equals 1 to n of x sub I, p sub I. So basically it says multiply your x and its probability, add up for however many you have. Okay. So for example, Northwestern University posts the grade distribution for its courses online. Students in Statistics 101 in a recent semester received 26% A's, 42% B's, 20% C's, 10% D's, and 2% F's. Choose a Statistics 101 student at random. The student's grade on a 4-point scale with A equals 4 is the discrete random variable x with this probability distribution. So the first thing we're going to do is create our probability distribution. So we have to say what x is. So it's their grade on 4-point scale. Okay. So we have X and our probability. So if we start with A represents a 4, B is a 3, C is a 2, D is a 1, and F is a 0. And then we have our percentages. So 0.26, 0.42, 0.2, 0.10, 0.02. We should double check that our percentages add to 1 just to make sure. So 26 plus 42 plus 20 plus 10 plus 2. And it does. So let's talk about some probabilities. So say in words what the meaning probability X greater than or equal to 3 is, what is this probability? So if we take our 4-point scale and convert it back to a grade, you're saying you get an A or a B. So you earn a grade of B or better. So we're going to say the probability you get a B plus the probability you get an A. So the X equals 3 plus X equals 4. Probability X equals 3 is 0.42 plus the probability equals 4, 0.26, which is 0.68. So 68% chance that you earn a grade of B or better. Okay. Write the event the student got a grade worse than C in terms of values of the random variable X. What is the probability of this event? So if you got a grade worse than C, it means that you got below a 2. Okay. It does not say that you got a C. So we are saying strictly less than 2. So that's the probability you got an F plus the probability you got a D. So probability you got an F, 0.02, plus the probability you get a D, 0.10, which means 0.12. So 12% chance you get a grade worse than a C. So next, we want to compute the mean and interpret this value in context. It is really important in the terms of discrete random variables that when you calculate mean, you also interpret what that actually represents in the problem. So our mean, which we usually denote now E of X, we take our X value, we multiply it by its probability, and we add. So the first X value is 4, the probability is 0.26, okay, plus the next one, 3 times 0.42, plus 2 times 0.2, plus 1 times 0.1, plus 0 times 0.02. Okay. So we can just plug it into a calculator at this point, and we get an expected value of 2.8. So what that means is, in the long run, we expect a random student to get between a B and a C in the course. It's actually more like a high C, a 2.8, pretty close to a B, but we're between 2 and 3. So 2.8 you could say is a high C+, but you could say between a B and a C, or you can say a high C in the course. probability. So next we have variance and standard deviation. So variance and standard deviation are not as fun or easy as mean is. So we go back to the distribution table. We have our values. It can take, we have their probabilities. So variance in order to calculate variance, the first thing you have to do is calculate the mean. And what you end up doing is for each x value, you subtract the mean, then you square it and multiply it by its probability. And then you keep adding. So then you would do the second value minus the mean squared times its probability. And you keep going for however many values you have. So for its formula, it's the sum of the values from 1 to n of each x sub I minus mu sub x squared times p sub I. Okay. And then the standard deviation is just the square root of that. So just like normal, where standard deviation is the square root of the variance, it does not change for discrete random variables. I'm not going to ask you to find variance very often, and when I do, it's not going to be for large tables. And then at the very end, I will discuss how we can do this on the calculator. Okay, so the daily lottery costs $1 to play. You pick a 3-digit number. If you win $500. Find the expected value of the lottery and the standard deviation. So first things first, 3-digit number here is 001 to 999. Okay, we're going to assume that zeros work in the lottery. So X is going to be our winnings. So when it comes to probability distributions, when you have to spend money to do something, you have to take that into account. So if I don't win, I actually end up with -1 because I paid $1, I didn't win anything, so I'm in the negative. And if I do win, I don't actually win $500, I win $499 because it costs me $1 to play. So when it comes to probability, there is a 999 out of 1,000 chance you don't win, and a 1 out of 1,000 chance you do. Because it's a 3-digit number, remember, think back to decimals, that's thousandths in probability. So that's why we have 1,000 in our decimal place, because it's the probability as a decimal to 3 decimal places. So our expected outcome. So we have -1 times 999 over 1,000 plus 499 times 1 over 1,000, which when we plug into the calculator is -0.5. So we're actually expected to lose, on average, 50 cents. So does not pay to play the lottery, where your only outcome is either you win $500 or you don't. So in order to find the standard deviation, I first have to find the variance. So that says take your x value, so in this case -1, subtract the mean, -0.5, square it, multiply it by its probability, plus, and then do it for your next x value. So 499 minus negative 0.5 squared times 1 over. This one's a little bit tricky because our expected value is negative, so it looks a little bit tricky, which when we plug into the calculator ends up giving us 249.75, which means our standard deviation is the square root of that, 15.8. So we have an expected outcome of negative $0.5 and a standard deviation of $15.8. So this is not a good game to play. Our last example, a pair of dice is rolled. Depending on the sum of the dots on both dice, Cole can win or lose money as shown in the following chart. Should Cole play the game? Explain your answer. So if you have a question like this, should you play means find the expected value. And if you're playing a game, you want to come out with an expected value that's positive, which means on average, you win. So X is going to be our winnings again. So if we do our table, so we can win $6, lose $4, win 7, win 5, lose 1. So remember, if you lose money, you have to denote it as a negative. All right, and then to get our probabilities, we have to go back to that table in our notes where we had all of the outcomes for the sum of dice. So getting a sum of 6, 8, or 9 is 14 out of 36. A sum of 2, 4, or 5 is 8 out of 36. A sum of 10 is 3 out of 36. A 3 or a 12 is also 3 out of 36. And a 7 or 11 is 8 out of 36. You can simplify these fractions. It makes it easier for when you're plugging into the calculator, but it's not necessary. So our expected value is going to be 6 times 14 over 36 plus negative 4 times 8 over 36 plus 7 times 3 over 36 plus 5 times 3 over 36 plus negative 1 times 8 over 36. So now it becomes plugging into your calculator. I'm going to be very careful here with the negatives. And we end up with an expected outcome of $2.22. So going back to what the question is asking us, should Cole play the game? Yes, because he is expected to make $2.22. I should include because in the long run, he is expected to make $2.22. If my expected outcome had been negative, like our previous example, no, don't play the game because you'll be expected to lose money in the long run. Let me know if you have any questions over discrete or continuous variables.